can still see each other. I must remember, am I not in the way of this? I have to stand here, otherwise I get in the way, yeah. Yeah. Fine.
So you'll talk for about 50 minutes?
45, I'll try and make it 45, I'll do my, oh yes, so hopefully a bit less now because
Give us 20 minutes for questions if we can.
Oh yeah, no problem.
So then I'll come back and turn the Zoom on for questions and answers. Gotcha.
So what we'll do, shall we just test the sound on the videos? Let me just quickly hop through. No, you're not supposed to see these.
No.
It's supposed to be exciting, unexpected.
Do it quickly.
Right, just
It
see.
looks amazing. Oh wow, look at that.
No, but no sound, so...
Oh, hang on, why is it
Unless I'm not got sound.
have you got your sound up?
Let's have a look.
It should be...
It's possible, that's possible. That's perfectly possible that I've goofed. Sound. That's interesting. It's not talking, the sound system. Sometimes you have to sort of flip them on and off a couple of times to get them to talk to each other. Yeah.
Nothing.
Not so far. Somebody needs to flip a switch somewhere else. So, but it's not allowing to change it, which is unusual. Let me just... That's a bit curious. I don't want to open the software thing. That's all right, let me just disconnect something for a second.
I don't think the riding's over there. Let me check. Tuesdays.
No sound. It thinks it's at maximum. Oh. That sounds like we've got there. Sounds a little bit too loud. Okay, fantastic.
Good.
That worked.
Yes, there was a button.
Okay, fine. Sweet, I'll turn it down a little bit. It was a bit deafening. It's very odd. I'll do it this way. Maybe about. Should be a bit safer and save everyone's ears. Just going to get a mouse out to make it easier for flipping the slides. That'll be.
institution, really. Next door to you, you've got one of the biggest private libraries in London.
Fantastic.
The reason most people join the stuff, I think there are about 25,000 bodies.
I'll go and do a toilet break first and then we're ready.
Let me show you. it's 8 o'clock, and we'll start our science group meeting. It's a special one this evening. I'm delighted to have David Parker come to talk to us about space. I hope you will not misunderstand me if I say David has been in space for 40 years. In particular, David, who did his first academic qualifications at Southampton University and now lives in Bristol, the European Space Agency, in its theoretical manifestation is based in the Netherlands. David has been involved with the European side of all sorts of exciting space projects, which he intends to talk about this evening. I warned him that his audience was likely all to be glued to their small black and white television sets, watching the Apollo 11 landings on the moon and saying, don't we live in a wonderful time, and over the next several generations we're going to be exploring the moons of Jupiter and moon Saturn and so on. So David will deal with all these particular problems, and with the extraordinary modern plans, notably the NASA-sponsored Artemis project, which is going to see a base on the moon being used eventually for travel to Mars and to the other planets. He's a real expert in the field. We're very fortunate to get him. David, the floor is yours.
Thank you, Pat. First of all, thank you for the invitation, the opportunity to be here. Those who've worked with me and seen my presentations elsewhere in the European Space Agency always know that I have too many pictures and too many things to say. So I'm going to launch into a kind of funnel that goes from talking about the European Space Agency, what that organisation is and what we do, very briefly, particularly talking about some of the scientific and space exploration activities that ESA does. I will say it straight away, ESA, the European Space Agency. ESA is an organisation that in the early 1960s, ESA was founded in 1975. The guy who negotiated the UK membership was somebody called Michael Heseltine. Ever heard of him? Michael Heseltine remains to this day a staunch advocate of the European Space Agency, amongst other things. I wanted to, yes, absolutely go back to Apollo. It answers to one of the questions that always comes up, which is why aren't we on the moon and why aren't we on Mars, indeed, given that we went to the moon in '69. I am a child of Apollo. I was, I always have to do the maths and it gets more difficult. Yeah, 6 years old in July 1969. When Buzz and Neil stepped on to the moon. Little did I know that years later I'd be having dinner with Buzz Aldrin in a bizarre restaurant in a hotel in Abu Dhabi. And the thing about Buzz, he just talks about himself all the time. He never asked anything about anybody else. He's a fascinating guy. I'll come back to Buzz somewhere at some point. But I want to absolutely talk about what's happening right now, why Europe, indeed the UK, is at the heart of the new era of space exploration, returning humans to the surface of the moon and preparing one day to go further to Mars. I want to talk about Mars a bit. I know you had a talk relatively recently. We think it was from Sanjeev Gupta. We're not quite sure, but somebody from Imperial College who I think I know about Mars exploration. That's very close to my heart. I spent past 20 years of my life trying to make a particular Mars mission happen that has faced many, many challenges, so we'll touch on that. But also try and explain why we're doing space exploration, because that's really, really important, and try and be a bit precise about it. So we better get going because I'm already consuming my time. The European Space Agency, it's an intergovernmental organisation. There's a convention, i.e. a piece of law. You will find that in the Statute of Westminster and all the other member states of ESA. There are now, it's grown to be 22 member states. It's nothing to do with the EU directly. Norway is a member, Switzerland is a member, the UK is a member. Not all the countries in the EU are in ESA yet. They are gradually accumulating. If you look at all the flags of the countries, that's the good game that I will lose, it's recognise all the countries that are members. There are several countries here that are not yet joined ESA, but are in the, if you like, accession states, and we'll do so in a little while. And you'll see the maple leaf of Canada there, because it has a cooperation agreement that goes back many years to work with ESA on many, many projects, and we work together very well with our Canadian friends. Canadian space policy has always kind of balanced the US versus Europe. They sort of work with both sides. Very smart. Okay, as I said, over 50 years of experience, 22 member states, 8 sites. I have spent my last 7 years based at the European Space Technology Centre. ESTEC is about, like a university campus, about 4,000 people located on a windswept site near the beach of Noordwijk, which is sort of between Amsterdam and The Hague. I've been living in Leiden, which is a fantastic city. It was boring people over dinner about that. Lovely city to live. But it's a very international organisation. My team was composed of people from all across Europe. And I have, between April 2016 and end of June of this year, I was the Director of Exploration at the European Space Agency. I reached 60 and I've kind of handed over the responsibility. I'm doing some other things now within ESA. Before that, yes, I was trained as an engineer. I worked in industry for many years in Bristol and then Stevenage, and then worked in UK government, helped set up the UK Space Agency some years ago, and was Chief Executive of UKSA until 2016. So I've seen space from different directions, and as an engineer that became, well, as I always say, a second-rate engineer that became a third-rate policy person, I've seen it from different directions from inside government, and that may generate a perspective that is not just talking about the science and not only talking about the cool technology. ESA is an interesting organisation. Unlike NASA, we do a lot more than NASA does. We don't spend as much money. The scale of what ESA does is much broader than NASA because we're heavily involved in telecommunications activities, developing technologies that you use every day. Does anybody know how they use the European Space Agency today? You're shaking your heads. You have. Have you looked at the weather forecast? 2/3 of the precision of the weather forecast today comes from meteorological satellites built in Europe, operated by the EUMETSAT organisation, built by ESA for them. EUMETSAT is the operational organisation that provides MET data to the world in cooperation with the US. So aircraft navigation relies on weather data, and the military rely on weather data. It's absolutely essential for military operations. But the weather satellites that we produce in Europe are absolutely top class. More than 60% of the essential data that we need to understand about climate change, the so-called essential climate variables, are only or best measured from satellites. And Europe, through ESA and the European Union, has constructed the world's premier set of Earth observation satellites looking down at planet Earth from the top of the atmosphere, pollution, the changing weather conditions, yes, but long-term change of the surface, the ice sheets, and the sea surface temperature, which is one of the main key markers. There's now a 35-year history of measuring sea surface temperature from European satellites. Absolutely essential for understanding climate change and what we're doing to the planet. The Copernicus satellites of the EU and ESA produce about 10 terabytes of data every day, and it's given away for free to the world to use in all its different ways. And Google, one of the main suckers up of this data and use it, but so do governments around the world. I don't know for you, you probably know your way here. I found my way here with the aid of my phone. My phone has satellite navigation system. Some people say GPS. What they mean is satellite navigation. GPS is one of the satellite navigation systems that we use. It's the US military system. You also, without realizing it, you're using the Russian system called GLONASS, which is also a military system. But you're also using Galileo. Galileo is the European satellite navigation constellation, and it's the only civilian-controlled global satellite navigation satellite system. And those satellites provide timing data, which we then use for navigation, and it's slightly more accurate than GPS, in fact. So ESA is doing all of these different sort of things, but I'm going to focus on the science and the exploration. I'm not talking about getting into orbit, operating satellites, mainly talk about the science and the exploration, because it's what's close to my heart and has been for a very long time. Now, within ESA, there is a program called the science program, and there's a program called the exploration program. So one of the interesting questions is what is the difference? Well, James Webb Space Telescope, Europe has built 1.5 of the 4 scientific instruments on James Webb, and particularly the instrument, the mid-infrared instrument, LED from the UK, which sees the furthest back in time. That is in the scientific program of ESA. As is Gaia. Gaia is a mission that is measuring the positions and locations of 1 billion stars in our galaxy and is unparalleled. Nobody else is doing the science that the Gaia spacecraft is doing. It's producing more scientific papers than any other space science mission, and more than Hubble and more than James Webb. And that's a 100% European project. But there are sorts of missions where we go out to the planets in the science program, which you might call exploration, and I would be happy to call them exploration. One of my most memorable days as being a UK delegate into to the ESA years and years ago, back in 2005, was being in the control room in ESOC, the Space Operations Centre of Europe, when Huygens probe landed on the surface of Titan. This is the most distant landing made by humankind anywhere in the solar system. Nearly a billion miles out on this crazy world. And when we saw the first images come back, fuzzy black and white images of the probe descending through this thick hydrocarbon atmosphere of Titan, we saw a world for the first time. We saw hills, we saw a coastline, we saw what looked like a river basin, but not of water, but of cryogenic hydrocarbons. If somebody could go there and exploit all the hydrocarbons, then maybe make a fortune. But an extraordinary world where it rains hydrocarbons and it's frozen lakes of these materials. A fantastic European achievement. Another fantastic European achievement nearly 10 years later, the first spacecraft, Rosetta, to go and orbit to a comet, to go and monitor a comet close up, and more to the point, to put a little probe onto the surface of the comet for a few hours of operation. But the Rosetta spacecraft followed the comet CG, or Churyumov-Gerasimenko, as it approached the sun, as it came from outer space and approached the sun. And for the first time, we saw one of these primordial bodies, I call them kind of leftover material from the dawn of the solar system, close up and personal. And Europe did that. Nobody else had done that before. And we're now, as Jim mentioned, on our way to Jupiter. This year, the Jupiter Icy Moons Explorer was launched from the European Spaceport in French Guiana, Kourou, on an Ariane 5 rocket, on its long journey to the Jupiter system, where it will study 3 of the ocean-bearing moons, the Galilean moons of Jupiter, and marking a new phase in trying to understand this complete system, which is almost like a miniature solar system. One of these, several of these places appear to have frozen oceans, frozen ice cover. There may be oceans underneath. They may be a place for life somewhere else in our solar system. Those are, we would consider to be scientific missions. Each one is not connected to the one that goes before. They're going to different places doing different things. Our exploration program are about campaigns of exploring different destinations, and destinations where human beings will one day live and work, or in the case of low Earth orbit, have been living and working for the past 20 years. So let me go historical for a moment. These kind of talks often feature pictures of things like this, Columbus, all sorts of questionable social consequences of European exploration. It's a particularly Eurocentric view of exploration. Allow me a Bristolian, a Brigstow perspective on exploration. I have lived, been my adopted home for the past 33 years, and we celebrate a guy called John Cabot, or who's actually an Italian called Giovanni Cabotti, who sailed from the harbour of Bristol in 1497, funded by the private sector, funded by the Bristol merchants trying to find a route to China. But I love and back in 1997, a replica of the ship was built and was sailed back across the Atlantic, because where John Cabot and his team ended up was what we now call Newfoundland, in Newfoundland. I had the pleasure to see the ship leave Bristol Harbour, go under the Clifton Suspension Bridge, and Concorde flew over it. And a few months later, I was in Newfoundland at a friend's wedding and saw it arrive there. But I like the picture as a space engineer, because this looks like an elliptical transfer orbit departing planet Earth, going to explore a distant location, arriving there, going around a bit, exploring the location, and then elliptical transfer orbit to come home again. That's this kind of engineer's view of the world. He just missed and landed in Brittany, so he came back to Bristol via Brittany, or maybe he wanted to pick up some duty-free, I don't know. Fantastic example of exploration. Historical exploration very often has a scientific content, often has a mercantile or economic content to it. And it also has, it's about going there and coming back again. Our scientific missions tend to go there and don't come back again. Generally, when we've got human beings, we want them to come back again. So the ultimate example, we've talked about it already, Apollo 11, picture of Buzz Aldrin on the surface of the moon in July 1969. So my joke question, and I've done this to the new crop of astronauts earlier this year in the European Space Agency, is in that picture, which two things are still operational today? Any guesses?
Laser reflector?
Wow, that nobody has ever correctly answered that question. Give that man another glass of wine. Correct. So this strange object here, so the answer is Buzz Aldrin. And the other thing is a laser retroreflector, which basically you point anybody who's got a sufficiently powerful laser, you point it at one of these devices. It exactly returns the laser signal back. It is used, they are still used for measuring precisely the distance between the Earth and the Moon, and it's one of the ways that puts to the lie that we never went to the Moon, because the Russians can do it, the Chinese can do it, anybody can point their lasers at the Moon or get a signal back, because there are several of these laser retroreflectors, and we're building a new generation, and there's a European one that's going to go to the Moon very, very shortly. The only scientist that ever been to the Moon was Jack Schmitt on the last mission, Harrison Schmitt on the last mission, Apollo 17 in 1972. He was a geologist, and he was the only scientist that went to the Moon. One of the things about the new era of exploration, many of the people that will go to the Moon will be scientists, or medics, or engineers. They will not just only be test pilots. Nothing wrong with test pilots, but there's more to it than that. But the question that gets asked is, if we did all of this stuff 50 years ago or more, why didn't we stay there? Why didn't we go on to Mars? Why aren't we on Mars with human beings already? Good question. The way I answer it is by talking about tea. So again, in Bristol, there used to be a Brook Bond tea factory. It's now an art gallery. And Brook Bond tea used to come in little boxes. I'm looking for recognition. Yeah, it used to be picture cards in Brook Bond, and you used to collect 50 of these picture cards and stick them into an album. That's my album of 1971, The Race into Space, man's first, and it was always man's first 50 steps into the universe. Most of the picture cards were about the story from Sputnik up to the Apollo moon landings, and the last few picture cards were what was expected to happen in the 1970s. So there was something called the Space Shuttle. There was something called Skylab, which turned into the first space station. There was something called the Grand Tour, which was a robotic missions to the outer planets. That became Voyager. And the last three picture cards was the lunar tug, the nuclear-powered tug to go to the moon and come back again, backwards and forwards. The moon base under the surface of the moon, a scientific base under the surface of the moon. And the very, very, very last picture card was of the human mission manned flight to Mars, which was going to leave in November the 12th, 1981, arrive at Mars in August 82, return in August 83. This was not science fiction. As I now know, there's a fantastic historian of the US space program. He's written amazing books, John Logsdon, about the Nixon space program. It was presented to him, the whole plan for the expansion of NASA through the 1970s, by his vice president. Anybody remember Nixon's vice president? I'm looking at the Spiro Agnew. Yeah, he chaired a panel that was working on a whole plan for the future of the space program in NASA. And it basically involved doubling or trebling NASA's budget to do this. Of course, Nixon had one or two other concerns in 1970, 71. There was a war going on. There was a massive, actually, social program that was being planned. And there are only two graphs in my presentation. This is the first one. They're both about money, because no bucks, no Buck Rogers. This is what happened to NASA's budget. It had peaked in 1966. By the time of the Apollo moon landings, it had already halved. It halved again, and this goes out to 2012, but it's still around 0.35, 0.4% of the US federal budget. So this is the discretionary spending of the United States at a federal level. And if I tell you that NASA's budget now is $22 billion a year, and that is only focused on science, exploration, Earth observation, it doesn't do any telecoms, doesn't do navigation, it doesn't do space weather, it does a whole bunch of things that ESA does. ESA's budget now is 7 billion euros a year, roughly equivalent. It tells you that NASA has a much, much, much smaller budget than it used to have, relative terms, but it is also still the biggest player on the block. And so the answer to the question of why didn't we do all of those cool things on Beyond Mars is just money. And what NASA was encouraged to do and was willingly embraced is international cooperation. And the ultimate symbol of international cooperation is the International Space Station. Originally in the Cold War era, it was going to be Space Station Freedom. And then it became the International Space Station after that's not good. The Berlin Wall came down. There we are, still there. The International Space Station is the most extraordinary human achievement to have built this very complicated machine weighing 400 tons out of pieces that were built in Russia, the United States, Japan, Canada, all across Europe. The main Columbus scientific module built in Germany. And all came together and assembled in orbit, traveling at 17,000 kilometers an hour, 400 kilometers above your head, and has become this place that has been permanently crewed now for 22 years. There have been a crew, and is now a 7-person crew aboard the International Space Station for 22 years. Is there anybody younger than 22? Probably not. Okay, but, oh, fantastic, yeah. So basically, your entire lives, there have been people living off-world. Think about that. It's an inflection in the history of humanity. There have been people living continuously off-world for the entire duration of those people's lives at the back. Thank you. So what do we do there? The International Space Station. I don't know why it keeps turning on and off. I'll keep waving things around. Maybe it doesn't, that's why. It's a place where dozens of astronauts have performed hundreds of experiments on behalf of thousands of scientists around the world. Actually, it's 240 astronauts have been to the International Space Station. I checked this morning, 243. We here in Europe have a particularly effective program of using the International Space Station. Interesting question. Does anybody know the gentleman on the right-hand side of that? No. If you were a French person, you would say it's one of the top 10 most famous people in France. Thomas Pesquet, two trips to the International Space Station, commander of the International Space Station, massive star. The French president takes him wherever he goes on an international trip to the US or wherever. It's still a very nationalistic thing that you probably know who Tim Peake is, but you don't know who Thomas Pesquet is. Thomas Pesquet has several million Facebook followers. But not just that he's a nice guy and he's very smart, and he was originally an Air France Airbus pilot. He's done some lovely videos you can go and search out somewhere on our YouTube site, talking about the science that is happening on the International Space Station. And we very consciously link the science we do to the United Nations Sustainable Development Goals. The SDGs should be embedded in every corporation, every organization, because they're about change, they're about encouraging the development of sustainable development of planet Earth. So I always give this simple example. You and I, here in Britain, we'll use about something over 100 litres of water every day. Different things, different purposes. You can work out what I'm talking about. With the current generation of recycling, grey water recycling as we call it, and recycling of CO2 and so on the ISS, the astronauts in the ISS use about 5 litres of water a day. Sounds pretty cool. But if we're going to go to the moon and one day onto Mars, you do your calculations of how much water a crew would have to take, 5 litres a day, the numbers don't stack up. If we're going to live on the moon, live on Mars, we have to get even better at doing this recycling stuff, even better at doing this circular economy stuff. So recycling anything and everything. We have an experiment in Barcelona, University of Barcelona, where basically there are 6 rats living in a completely closed life cycle system, where everything is recycled. Everything is recycled. And it's 6 rats, because 6 rats roughly equals 1 human being. It's not something we're ready to use yet, but it's spinning off technologies which are being used all over the place. I don't have time to explain all of them. I'm happy to do so in the Q&A session. But you have to take my word for it that these technologies are coming back to planet Earth and being used in everyday life. Our astronauts are kind of the tip of the iceberg. We've had, and European Space Agency, a series of astronaut missions to the ISS. Tim Peake's back in 2015, 2016. Most recently, right now, aboard the International Space Station is a European astronaut with a Danish passport. Andreas Mogensen is currently the commander of the International Space Station. Again, is somebody with, in his case, with an engineering background. He's not a pilot, he's an engineer by training, and he's currently commanding the International Space Station. Our current core of 7 astronauts are just being expanded. Last year, we selected a new group of astronauts, a long campaign. We had 22,000 applications. So the process of whittling, and just to apply, you had to have some basic aptitude and demonstrate a higher degree. You had to have a higher degree just to apply. We whittled this down to a new group of astronauts, and it happened, I won't go through all of these, there happens to be, we selected 5 new career astronauts that entered training at the European Astronaut Centre in Cologne in the spring of this year. One of them happens to be Rosemary Coogan, who's a Brit. There's another Brit called Megan Christian, who is in the Astronaut Reserve. And a project that's really close to my heart was to broaden the representation of people who go into space. And we selected somebody called John McFall to be a candidate first astronaut who happens to have a physical disability. John lost a leg in a trauma accident when he was about 19 years old, prevented him from going into the forces. His life fell apart at that point in the early 20s. He rebuilt it to become a British Paralympian bronze medal winner in 2008, getting at the 100 metres, 12 seconds with one leg, and an artificial leg. Is anyone could run 12 seconds? No? Okay, in this room. And John then went on to become an orthopaedic surgeon, and he's now in training in Cologne with a view to flying him on a real mission. So, having talked around the subject a bit, given you some hints, this is my kind of analysis. Why explore? I give you basically 4 reasons. New knowledge, which is science, but it's also understanding and capabilities. It's the possibility to do things we haven't done before by going out to places. It's the technological innovation and the economic value. I can show you graphs, and maybe I'll bore you with it. When you give me a euro or a pound or a Swiss mark or whatever it is, we return about 3 euros or pounds or Swiss marks of economic activity. So when that is taxed, it basically pays for itself because, you know, tax rates are around 25, 30%. It's essentially self-funding. The more we do, the more opportunities there are. But everything we do in exploration is pretty much through global partnerships, and it's also helping us tackle these global challenges of the changing environment, of tackling the challenges we have of using resources sustainably. And then nothing more inspiring than the astronauts to inspire the next generation. We always joke that if we could find dinosaurs on Mars, that's the perfect way of inspiring the next generation. We want to, what we're doing, and we hope through all of our different activities, attract people into the world of science and technology, convince them that it's something that's a career worth pursuing. Only a fraction of the people will ever come into the space industry, and an even smaller fraction may become astronauts. That's not the point. The point is the world needs smart people taking on big challenges, even more so than ever. So I give you those 4 reasons to do exploration. Where are we exploring? I said it's about places where human beings can credibly live and work. So we can't credibly talk about sending humans to the moons of Jupiter. They'd be fried by the radiation, let alone going beyond our solar system. So really now it's about these three destinations. Our backyard, being low Earth orbit where the space station is, where it's a place to live and work in space. It's a few hours away. It's accessible. It's now affordable. Any university can fly a little scientific payload up to the International Space Station for about 50,000 euros now. So any university pretty much can find the way to do that. It's possible to send something into space now and bring it back again as well. The moon, very, very interesting. I'll focus on that because I want to focus about the Artemis program. Our planetary backyard, why is it interesting? I like to say the moon is a museum of 4.5 billion years of solar system history. It's hardly changed during 4.5 billion years. But with Apollo, basically we went to the museum gift shop, grabbed a few souvenirs, came home again, forgot about it. We've learned a lot more through our robotic missions to the moon since then that makes it a much more interesting place to go back to. I'll try and convince you of that. The moon is fascinating because it hasn't changed very much in 4.5 billion years. Mars is fascinating because it's changed out of all recognition. It started off with all the same raw materials as planet Earth, and life got going on this planet in the first billion years, as far as we can work out of its 4.5 billion year history. And the environments on the 2 planets were much the same during those first billion years. There was no oxygen, there was no plants. Life started here. Could life have started on Mars? Does it come from a common source? Did life start on Mars and come to Earth, start on Earth, go to Mars? We've no idea right now. We're just starting to scrape these kind of questions. The previous talk, I guess, about Mars exploration would probably gone into a lot more detail about this. But basically, Mars, I like to say, broke down. It lost its protective magnetic field. The internal core stopped rotating, so it lost its protective magnetic field that keeps you and I safe day in, day out from cosmic radiation, radiation from the sun. Its water was either lost to space and continues to be lost to space, or most of it got frozen as the planet got too cold. Most of the water is probably believed beneath the surface. We've been measuring it now from our spacecraft. But as an ultimate destination, to understand whether life got going somewhere else in our solar system, only humans are really going to be able to fully answer those questions. But it's a long way to go, and it's very challenging to send humans there even now. Our technologies, we know now how much more difficult it is to do than we did 50 years ago, so it's not going to happen tomorrow, whatever anybody likes to say. This is a busy picture because it's kind of showing you things, pieces of spacecraft and elements of our campaign of exploration to these 3 destinations. The International Space Station will continue to operate to the end of this decade and maybe into the next decade as our permanent foothold in space. For the next few decades, in my view, the moon is going to be the focus for human exploration, but actually a combination of robots and humans. There's an armada of robotic missions that have gone into orbit around the moon over the past 20 years. There's an armada of robotic missions that are on their way there for the next few years, and then the human return will happen by the end of this decade. For now, Mars is the home of robots, and I'll say a bit about that, but not too much. So let's go forward to the moon. The cartoon is trying to emphasize the idea of the humans and robots working together. But let me just focus on one example of what we know about the moon now that we didn't know. I've had the great pleasure of going to Johnson Space Center in Houston, which is the repository for the lunar samples brought back from the Apollo missions. And there are literally hundreds of kilograms of lunar samples that have not yet been opened and not yet fully examined, because the techniques are continually improving to examine these samples that were brought back, and you can now analyze down to the level of a grain or down to the atomic level with giant sort of synchrotron radiation, giant microscopes, all sorts of things. The robotic missions realized with their orbital instruments there appears to be a lot of hydrogen in one form or another bound up in the rocks of the south polar regions and to some extent the north polar regions of the moon. And further analysis suggests that's essentially water. And going back and reanalyzing or analyzing rocks that have never been sampled before on the surface of the moon, we can see that there's tiny quantities of water bound up in the rocks of the moon. But more tantalizing is the possibility there is bound up in the regolith, essentially a slushy ice of water and other volatile materials. So why is water interesting? Well, water means life. It's the origin of life. It's fundamental to life. Water is also something astronauts could drink. It's also something they could synthesize hydrogen and oxygen from, and hydrogen and oxygen is a rocket fuel. So it's scientifically interesting. Where did the water come from? Is it isotopically the same as the water on Earth? Is it different? We went all the way out 1 billion kilometers on Rosetta to go and find a comet. Over the past 4 billion years, maybe the crashed comets sitting on the surface of one of these south polar regions of the moon. We believe there are regions that essentially never get sunlight, so what we call cold traps. They're incredibly cold temperatures that would, over periods of time, effectively act as a piece of blotting paper for water. So we need to go there. We need to explore the moon. We need to explore the water on the moon. It's only a few days away, as opposed to these missions that take years to go to the outer planets. But it's also a foothold for exploring permanently. So we talk about different sorts of science, and the way to think about it is we have scientific laboratories in Antarctica. UK has one. The Canadians have them, the Americans, the Russians, the Japanese. Everybody has scientific bases there. All sorts of science is going on in Antarctica. Drilling for ice cores, telling us about the history of our planet and now about climate change. It was totally by accident we discovered the hole in the ozone layer through scientific measurements in Antarctica. My vision and the vision of the space agencies is something like an Antarctic research base on the moon will be the next step. It won't be hundreds of people or thousands of people living there. On the contrary, it'll be a very, very harsh environment. But we just don't know all the science that we will do there, just as we didn't know the kind of science that we are now doing in Antarctica. And I make the comparison to the race to Antarctica, 1912, Scott, Amundsen, racing to the South Pole. After that, nothing really happened. Nobody went back there until the 1950s. And it's kind of the same thing. We're about to enter a new period of sustainable lunar exploration. It will be slower, because we don't have the money on the scale there was in the 1960s. The point about it is to do it in a way that is sustainable over a much longer period of time, rather than just one-shot missions. Part of the element of that is the Artemis program, and I don't have time to talk about the Chinese space program, but there is a broadly equivalent set of activities in China that are now happening as if you like, the number 2 space power now. We're returning humanity to the moon, but this time NASA is not doing it on its own. The US is not doing it on its own. It's with the European partners, the Japanese, the Canadians, the Australians. Very many other countries are now involved in the Artemis program. This is the rocket, the space, very boringly named Space Launch System. This is the first launch that happened last year, November the 16th. An uncrewed test flight of the whole vehicle, the biggest, most powerful rocket that has taken off and gone into orbit so far. It's more accelerating power than the Saturn V. And on top of it is the crew vehicle that's called Orion. Again, it's a nod to Apollo. The Orion crew vehicle, classic conical design, it carries a crew of 4 rather than the 3 in the days of Apollo. And Europe is building the power and propulsion for this, the so-called service modules. So provide the electrical power, the propulsion, the water, the oxygen to support the astronauts. And this is the first time that anybody other than the Americans have been on the critical path of building the hardware for NASA's human space program. So basically, NASA cannot go to the moon without Europe now. So the European service modules, the first one was built and launched, the second one is ready to go, the third one will be delivered beginning of next year, and there's a production line now across Europe building these service modules Each one, the whole launch mass of the Orion vehicle sitting on top of the rocket is about 27 tons. About half is the capsule, about half is the service module of power and propulsion for the Artemis missions. They will happen roughly one a year when we get up to speed. This is the path of the first mission last year, a 25-day test mission that took the spacecraft actually not just to the moon, into orbit around to the moon, but actually beyond the moon, some way back. I was able for the first time to get rather iconic pictures of from a human space vehicle of the moon and the Earth in the same picture. And I'll show you, you'll see those in a couple of videos I'm about to show you. And so why not, let's go on to the amazing mission of Artemis 1 last year. Launched 16th of November, 25 days, traveled 2.3 million kilometers. And you'll see the rocket launch, the Orion vehicles separate from the upper stage and the various steps of the mission. And let's hope this all works when I press the go button. It's quiet again. What's happened? We've lost the sound again. Rats! There should be lots of lovely sound here. Okay, I will talk instead. You might have seen what looked like an astronaut. It's a fully... Oh, it's come up again. There's a dummy astronaut aboard, plus Snoopy and Shaun the sheep. So the first European astronauts to go to the moon was Shaun the sheep from Aardman Animations in Bristol. They had the pleasure of returning there after a successful mission to the moon. So you see, this is the outward trajectory coming back, swinging by the moon. This is my team in Operations Centre in the Netherlands, and return to the Earth and successful splashdown of the capsule. I was able to watch this, and amazing the technology. I was over the mid-Atlantic able to watch this on a satellite connection. It would have been impossible 50 years ago. And little Shaun was safely returned to Aardman Animations earlier this year. So it's just the first step. Somewhere towards the end of next year, beginning of 25, we'll have Artemis 2. We'll have 4 crew, 3 NASA astronauts and 1 Canadian astronaut on the first flight, effectively recreating Apollo 8, but for a longer duration. Whoops, go on. But I said about sustainability. So rather than just building everything, throwing it away, what we're going to do is build a kind of sustainable spaceport around the moon, something called the Gateway. Gateway is kind of like a mini space station, able to accommodate a crew of 4 at a time and live and work in orbit around the moon, and act as a kind of node to collect the robotic missions and the human missions together for going down to the surface of the moon. Gateway is, again, an international project. There are 3 habitation modules. 1 is being built by the US, 2 of them by ESA, by Europe, and this will be launched towards the end of this decade as a permanent base throughout the 2020s and the 2030s. If you think of exploring like Mount Everest, you talk about a base camp. This is kind of like the base camp for exploring the moon, except upside down in the sense it's at the top of the gravity well as opposed to the bottom of the gravity well. And so a permanent place for our long-term exploration of the moon. It's in a very interesting orbit, I can bore you with that. It will do science when there are non-astronauts there. Most of the time there won't be astronauts there. There will be science going on robotically whilst waiting for the next Orion vehicle to arrive. Another robotic thing that we, Europe, are contributing to this overall Artemis program is something called Argonaut. Argonaut will be our, if you like, Amazon delivery truck, a robotic lander but designed to support human exploration, taking 1.5 tons of science or technology or food or water, whatever is needed in support of the sustainable exploration program. It's one of the next European contributions to the program. We're right in the middle of selecting the industry to do that, but there will certainly be UK involvement in the Argonaut program. And the aim is the first launch by the end of this decade as well. So this is in a scale that is bigger than the small scientific landers that are being built at the moment by NASA, not as big as the human landers that will take the astronauts down to the surface of the moon. It's kind of in the Goldilocks zone that we, Europe, think we can contribute. And I talked ages ago about this idea of sustainable exploration, and when you combine Gateway, the robotic missions, the human landers, it gives you a flavour of this idea of sustainable human exploration. And this is the European concept for a sustainable moon base. in which the pressurized modules that support the astronauts are surrounded by a layer of regolith, of lunar material that is effectively used as a building material. And so I talked about using the water on the moon. We can certainly use the materials of the moon as building material. And some of our scientists have been working on sintering, or basically microwaving, simulated lunar material to make rocks, to see whether it's feasible to do that. The kind of cutaway picture here gives you a flavour of what the inside of the moon base would be like. It's not a firm decision. There's no firm decision to do this. It's our aspiration. Every 3 years, we go back to our member states and ask for the money for the next 3 years. So basically, so far, we've asked for the money until 2025. For this, we're talking about well into the 2030s, so it's not a firm proposal yet. But it gives you a flavour of where we're headed in the lunar exploration programme and why I make the comparison, and you'll see some pictures in a moment, with the Antarctic research bases that we have now. It'll be a similar sort of environment. I don't want to leave this talk without talking a bit about Mars. Again, I understand you've had a talk relatively recently about Perseverance and the NASA Mars exploration program. Mars is a fascinating planet, as I think I've hinted. We Europeans have 2 spacecraft in orbit around Mars. Mars Express went there on Christmas Day 2003. And since 2016, our ExoMars, Exobiology on Mars orbiter, has been in orbit. It's the kind of penknife of Mars exploration. It is acting as a data relay for all of NASA's Mars missions, but it is also on a trail of a mystery, which is what some of the trace gases, the very small quantities of interesting gases that are in the atmosphere of Mars. NASA's Curiosity rover claims to have discovered methane in certain regions. Methane is interesting. 2 sources and potential sources of methane. One could be life, one could be entirely non-organic geological processes. Our orbiter, which is incredibly more accurate detector of methane, it is not seeing it. Now, these 2 discoveries are not necessarily in conflict with each other. It could be there's a process that is locally producing methane and it's getting destroyed much more quickly than we think it should be destroyed. So this is a perfect example of where a robot on the surface of Mars and a robot in orbit around Mars are on the trail of a mystery, and we're not at the end of this mystery. The ultimate mystery is whether there ever was life on Mars, and we Europeans have been on a trail, and a very, very, very difficult trail for nearly 20 years to get the Rosalind Franklin rover, named for the 3rd scientist that was involved in the discovery of DNA, but was not recognized by the Nobel Prize system back in the 1950s. Rosalind Franklin rover is the first attempt to get below the surface of Mars with a drill, 2 meters below the surface, to get to material that might not have been destroyed by radiation over millennia. We're going to a destination that is about a lake bed that is about 4 billion years old. The original project was going to be purely European. Then we went into cooperation with NASA. NASA, for various reasons, pulled out in 2012. And therefore, we reconstructed this mission in total cooperation with the Russian space agency Roscosmos, with the Russians providing the launch, Europe providing the spacecraft to get to Mars, the Russians providing the lander to get to the surface of Mars, and the Europeans the rover. And we were due to launch on September the 20th last year. I think you know what happened. It's one of the most difficult experiences of my life, was having to propose to the Council of ESA that we discontinued this cooperation based on the advice of everyone. And so, having not being able to launch it last year, we are going to reconstruct the mission, build our own lander, which will take another 6 years. And we're working with NASA to launch the spacecraft to Mars, hopefully by the end of this decade. But as I keep saying, we've been waiting 4 billion years to solve this mystery. We can wait another 6 or 7 years. We have to be patient. And I think maybe the last talk also talked about this cooperation we have with NASA for Mars sample return, which is to bring pristine material back from Mars. Why do we want to bring rocks back from Mars? Isn't it cheaper to do the science there? It's the sort of question you get asked. This is a hideously expensive project. It will hit probably about 10 billion to get to get maybe a kilogram of perfect Mars material back over a 20-year period. It's a lot of money, but it's spread over a long period of time. But a very simple thing that we'll be able to answer amongst many, many, many different ones. I keep saying that, like Rosalind Franklin, we're going to a 4 billion-year-old lake on Mars. Well, we don't actually know it's 4 billion years old. The way we know we think it's 4 billion years old is because a bunch of PhD students count the craters on the surface of Mars, the distribution of craters, i.e. how frequently, how often stuff has hit Mars over the past 4 billion years. And they extrapolate from the only piece of actual data we have, which is the age of the rocks we brought back from the moon into the Johnson Space Center. Because we've actually been able to analyze the age of the rocks from the moon, and the students that counted the craters per square kilometer on the moon have done a lot of extrapolation, have estimated the history of everything on the history of the surface of Mars, as we've estimated the history of everything else in our solar system. But the only piece of solid data we have so far is the rocks we brought back from the moon. So it's why we want one simple example of why we want to bring stuff back from Mars. There are many, many other good reasons. This is really a fantastically complicated mission. We Europeans, it's multiple launches. The first spacecraft, the Perseverance rover, is gathering the samples, putting them into tubes about that long right now. We are building a robotic arm that will take those samples, load them into a container a bit bigger than a football, put them inside a rocket, launch that rocket off the surface of Mars. When that rocket is in orbit around Mars, that sample container with these precious samples that we've taken 20 years to gather will be thrown overboard and put into orbit around Mars, where our European spacecraft, the Earth Return Orbiter, will come along and scoop them up, make the first return trip from Mars back to planet Earth. Those samples will be loaded into a kind of re-entry vehicle, which will crash down on the surface of the Earth without a parachute, at full speed into the Utah desert. Because we don't want to have the risk that a parachute might fail, so we have to design the system that it can land at full speed, so why bother taking a parachute in that case? It's a kind of engineering logic which we have to solve in doing these missions. Having said all of that, it sounds bonkers. Maybe it looks even more bonkers when you see the video that tries to capture this. Starting with the Perseverance rover that is already on Mars, and the next landing of a NASA second lander that will pick up these samples. Yeah, the music seems to cut in after a few seconds, it's fine. So the Perseverance rover will be able to watch something landing on Mars for the first time, and will then bring its samples in a kind of test tube rack of these containers, where our robotic arm will one by one pick them up and load them into this sample container that I described, probably about 25 samples, seal them, because one of the things we have to do, this pass the parcel game, is to avoid anything from Earth contaminating those samples and avoid anything on Mars contaminating Earth. We call it planetary protection. So yeah, we take off from the surface of another planet for the first time, and separate in orbit around Mars, and then the sample container on the upper stage is released into orbit. So it's this big, it's in orbit 400 million kilometers from planet Earth, and this enormous spacecraft, and it is enormous, the biggest thing we've ever built in Europe, has to scoop it up and find it. It's, for engineers amongst you, it's 30 kilowatts of solar power and a 1 Newton of electric thrust to bring it all the way back again. This is the first time you have to spiral out of Mars orbit and come back to Earth. And again, Europe is on the critical path. It's only going to happen because we are doing it. We're doing it with the US for the first time. It's a project that has all sorts of problems, and you may read about the challenges it has right now. But as an engineer, I'm convinced it's worth doing, and the scientists are utterly convinced it's worth doing. So having said all of that, imagine how much more complicated it is to send humans there and back. That sort of gives you the flavor. So we wave our magic wand and say, one day the humans will come. building a rocket to send humans to Mars is probably the easy bit. It's how do we ensure the astronauts arrive fed, watered, in a condition that they can go from 0 G of 6 months, a year, going to Mars and be able to work on the surface of the red planet, survive a landing, and bring them all home safely again. There's a lot to do. So my last few slides, I am coming to the end, I promise, is to say how some of this work is going on right here now. That's not Mars, that's Lanzarote. This is some of our scientists training astronauts, including NASA astronauts, to be geologists, taking them to what we call analog environments. They're fantastic analog environments of different places on the Earth that can simulate different places on Mars. I talked a lot about these Antarctic research stations. This is the Italian-French Concordia station in the high Antarctic desert. And we send scientific experiments and a medical doctor there every winter over season. So there's an ESA space guy or gal working in Antarctica as we speak. They do all sorts of experiments, ice cores, looking at the history, understanding developing the technologies, grey water treatment systems, recycling systems in Antarctica. But there are an awful lot of psychological experiments. Being isolated in Antarctica is a pretty good analogue for the journey to Mars and coming back again. The human factor in exploration is enormously important. I'm an engineer, so we talk about technology. We also have to talk about the people. Can we keep them safe and a part of a team? When we select our astronauts, we need people who can be leaders, but also followers, and can flip from one second to the next from being a leader to a follower. And we have explorers in the laboratory. This is Alexander Maurice and Beth Lomax, two scientists working in a laboratory at the European Space Technology Centre, kind of doing alchemy, extracting from simulated lunar soil the oxygen that is contained with it. A lot of lunar material is oxygen, and a process has been developed to take the left-hand side is what you're left with, the right-hand side is what you start with, simulated lunar material, extracting the oxygen one day to use in our rockets, one day for astronauts to breathe. So explorers are not just the ones that go out there, they're also in the laboratories. So I'm not going to bore you with all of these numbers. I'm not going to even bore you with the budgetary numbers. I want to just conclude by putting it all together with the story of Europe's space exploration program today. One of our most recent astronauts, Samantha Cristoforetti, on her way to the International Space Station last year. Thomas Pesquet, I mentioned earlier, Alex Gerst, who is a geologist, Matthias Maurer, who's an engineer, Tim Peake, who is a test pilot, Andy Mogans, who is an engineer, who's now on board the space station right now, Luca Parmitano, an astronaut. And this is the engineering teams building European service modules across Europe and installing and integrating it with Artemis 1 last year and launching it to the moon the way I've already shown you. And then stepping a little bit beyond this first Artemis mission, starting to talk about the assembly of the Lunar Gateway. Right here, just like we built the space station in pieces, it'll take 2 or 3 different launches to assemble the gateway and orbit around the moon. And one of the other things we will do as the astronauts return to the surface of the moon is to install a navigation and communication system around the moon. We want to have a network of satellites that will provide communications and navigation information to support the astronauts, but also to support the landing of our Argonaut landers. This is the Rosalind Franklin rover under test. The whole thing was built in a sterilised environment. This is demonstrating the drill that we hope will get those crucial samples on the surface of Mars. Parachute tests occurred successfully a couple of years ago. And the dream of returning these first samples back from Mars as a precursor to one day this ultimate goal, which is still years in the future, of putting the first humans on the surface of Mars. And we call this program Terrae Novae, meaning New Worlds. So thank you very, very much for your attention and inviting me here this evening.
Thank you, David, for a wonderful presentation. It gives us an idea of the excitement and the challenge which we're all going to face, the generations are going to face in the century to come. I'm sure there are lots of questions. If you want to ask a question, please raise your hand, and I'll bring the travelling flag along.
And there are no such thing as stupid questions, only stupid answers. Yeah, I can hear as well. That's good.
This morning in the Financial Times was a letter from Professor Keith Hayward, Fellow of the Royal Aeronautical Society.
Yep.
And the last few lines of it were quite interesting. He says, this has left the UK, he's referring to civil aerospace research, with at least one world-class manufacturing capability. Would you agree with that?
Well, you're talking about aeronautics rather than space now. He's referring, I suspect, I should say the RAES is my professional body, to the design and development of wings. So every Airbus that takes off on a wing designed in the UK, and the design and the manufacturing wings is, if you like, the remaining crown in the jewel of the British aircraft industry that once was number 3 in the world. Yeah, I could express lots of opinions that are outside of my remit on the topic, but that's what he's referring to. But in space, the UK is a player. It's number 4 in Europe, behind France, Germany, and Italy. But we have an outstanding commercial space industry. Inmarsat is based in the City of London. Insurance of Space is in the City of London. Surrey Satellites were the pioneer in small satellites and have educated people from all around the world in how to build small satellites. And you may not know there's a company in Glasgow that is churning out spacecraft the size of a shoebox and launching them, literally hundreds of them, for monitoring weather and doing all sorts of space technology demonstrations. So, and that Rosalind Franklin rover, I should say, was assembled, a few miles up the A1 in Stevenage. So there is a fantastic space industry, and it's in UK, and it's a bit of a well-kept secret.
Thank you. Question?
Okay, so just a question about the lunar base that they're maybe going to put on the moon. Do you anticipate that they're going to run into any legal difficulty? Because isn't it against international law?
How many hours have you got?
You can't take land on the moon, and no country can own land on the moon. Isn't that in this international treaty? So isn't it going to be a little bit difficult?
Correct. What you're referring to is space law is a fascinating area because nobody's ever taken anybody to court about space law because which jurisdiction would you do it? But there is a thing called the United Nations Outer Space Treaty of 1967, which basically prevents, as it were, owning an asteroid or whatever. But equally, it absolutely does not prevent you going to planetary destinations and indeed doing things there one way or another. So an analogous way of thinking about it, and it's not a perfect one, is who owns the fish in the sea? The answer is, once you're in international waters, kind of nobody does. So you have the possibility to take fish out of the sea without owning the sea. And it's kind of similar to the space law context. There are different views about this question of using space resources in particular as to whether the use of space resources is or is not prevented by that treaty. There is something called the Moon Treaty, which a small number of countries have signed up to, which is more explicit and is generally disowned by most spacefaring nations now. And oddly, in the absence of there being a very clear legal basis, I said this would take a while, the US have launched something called the Artemis Accords, which is a kind of recognition, it's an implementation of the UN treaties, an understanding of how to interpret and use those treaties, which many countries are signing up to now. It's not about being in the Artemis program, it's about a common understanding of the legal basis. And the odd thing is, there are 1 or 2 countries that have signed up to the Moon Treaty and the Artemis Accords, even though they're in conflict with each other. So it's a really interesting topic, and there are people who understand it a lot more than I do.
Thank you for that. Next question.
You mentioned the size of the budget quite a lot. What's the forum in which the amount that Europe is prepared to spend decided in? It isn't a thing you read in the newspapers a lot.
Well, every 3 years, the answer is, if you read the newspapers in France, Germany, Italy, and most of the rest of Europe, it's usually discussed. So there's a thing called the Council of ESA. I work for the executive of ESA. In other words, I'm an international civil servant. I'm employed by ESA. The Council of ESA are the delegations from those 22 countries. So the UK is represented by the UK Space Agency and the Department of Science, Innovation and Technology and Foreign Office and whoever it needs to be. And basically, every 3 years, that council goes up 1 notch and the minister arrives. And the ministers sit around the table and basically decide the funding for the next 3-year period of all of these different programs. Now, it's not, by the time you get to that day, most of the decisions have been taken, but it is, I've been to enough ESA ministerials to know it goes on into the middle of the night, let's put it that way. And you never quite know how it's going to turn out, and which programs get funded and which programs don't get funded.
Isn't it surprising that for a multi-trillion euro economy, we can only afford 8 billion a year? Mm-hmm. It seems to be out of proportion for something which you've portrayed as very important.
It's about 10 euros per head of population per year, something like that. It's of the whole space program, so there are some EU space programs, there are some national space programs. So per head of population, it's a lot less than the US. The bit that I've been responsible for, the space exploration program, I've doubled the budget from 450 million to 900 million euros a year. So 900 million, well, what would you say? So this year it's about 800. So it's about £1.20 a year per head of population. So I don't know what you can buy. Can you buy a stamp still for about the price of a first-class postage stamp per year per head of population?
Thanks. It was a fascinating talk. But it was obviously about ESA, but you didn't. I'm rather surprised you talk about space and not mention SpaceX or India at all.
Oh yeah, I could talk about China. I could talk about India. Talk about the Japanese. All of these different space programs. Yes, India has an incredibly ambitious space program. China has an incredibly ambitious space program. Elon Musk, SpaceX have technologically turned things upside down by being able to demonstrate successfully reusability of their launch vehicles, which has meant that they are now the #1 launcher of things into orbit. Most of the development money came from the US Department of Defense and NASA. The engine development came from NASA originally, Pintle engine development originally. But what he has done is get a bunch of incredibly smart people together, work them really, really, really hard, and adopted a different approach, which is to build a little, test a little, blow things up, keep trying, keep spending the money. But probably 10 billion of US taxpayers' money has gone into SpaceX so far. And the US is continuing to fund in parallel the Space Launch System as a government program and another commercial launcher, Vulcan, because they don't want to be dependent on a monopoly. Most of Elon Musk's launches is for the Starlink system, the global internet from the sky system. which I think has about a couple of million subscribers now, and he's spent several billion on it. So it's probably not yet breaking even, let's put it that way. But it's enormously ambitious. But yes, the technology has turned things upside down, absolutely. Yeah. And we use it. Our astronauts are launched on SpaceX rockets. Some of the cargo gets to the space station with SpaceX rockets.
Thank you. I have a question about the particular landing site on the moon.
Oh, yeah.
I think country choose different landing site. Is that right, that the dark side is more difficult to land, and then the resources and the samples you can pick from there is much more valuable?
Okay, so what you're referring to is the far side of the moon.
Yeah, the far side.
Yeah. So scientifically, the far side is interesting. There's a thing called the South Pole Aitken Basin, which is the largest impact crater that we've so far found in the solar system. So if you want to understand the history of the moon, this impact crater is sufficiently deep to have excavated material that we can't see anywhere else. So it's one of the destinations of some of the robotic missions. Robotic sample return missions will certainly go there. The most interesting regions scientifically are not so much the far side as the South Polar regions. That's where everybody's interested in going. Probably the first Artemis missions will go to an equatorial site, but as soon as possible we want to get to the South Polar regions. That's where, if we're going to have a permanent moon base, that's where it's likely to be.
And which countries and which year roughly you think we're going to happen?
Oh, okay. My view is that international politics and the pride of the US is such that they will return to the surface of the moon before the end of this decade. It will not be next year, it will not be 2025. Elon Musk has a contract to build a human lander system. That system requires between 8 and 12 launches and a rendezvous in orbit around the Earth and rendezvous around the Moon. I don't think that's going to happen in 2025 because the rocket hasn't even taken off for the first time yet. I have no idea what the timescales of the Chinese is, but it's around 2030. So we are in a kind of second race to the Moon. Ideally hope that it will end up in a cooperative activity. But the Chinese program is going at a pace. They've done something which we are planning to do, which is to demonstrate a telecom relay satellite that allows communications for the far side of the moon. We're planning to build a constellation of satellites, which means 3 or 4 satellites called Moonlight, which is a European program to provide global communications and navigation to the moon by the end of this decade. So there's a lot going on, and the Indians are going, and the Japanese have a lander that's on its way to the moon right now, a small lander. There are commercial landers, etc., etc. Israelis, yeah, Japanese, Americans, Europeans, everybody's going to the moon. Again.
Question?
Okay, so with all this talk of like launching like the Starlink satellites, the constellation satellites and stuff into space,
Yep.
are you guys also looking at like the increasing space junk problem?
Yes, so this is a completely other topic, but sustainability of the space environment is a real challenge. We have to move the space station from its orbit up or down increasingly often now because of bits of space junk. So it's not just once a year, it's several times a year now. A significant portion of the, a fraction, 1% or something, of Starlink satellites have already failed. There is a requirement current requirements, you should be able, that any satellite will deorbit within 20 years of it coming to the end of its life, passively, in other words, by getting sufficiently low, the atmospheric drag pulls it back down again. Not everybody is following that, and that includes the Americans, the Europeans, whatever, but we're getting much better at it. We have a program in Europe, and there are several commercial companies now that are going to demonstrate the active debris removal. So they're actually going up there, rendezvousing, grabbing something, and then bringing it back down again. Dead satellites, dead spacecraft, dead rocket stages. And the management of the space environment is a really big growing headache, monitoring it, understanding it, monitoring what other people's satellites are doing. If you follow it, it's not secret that some satellites of one country have mysteriously got close to other people's satellites and then moved away again and gone round them and come back again. No idea what that's about.
That gentleman got most of my questions, one of my questions,
Okay,
in terms of are we just running out of space for geosynchronous orbits and so forth. The other question, which may be a bit silly, but does Mars not rotate like Earth does?
Yeah. The Martian day is not the same as the Earth day, absolutely, yeah.
So,
and the Martian year is about roughly two.
Okay, so anything you put on Mars is going to have to cope with Martian light?
Different environments, yes. So, and it's particularly difficult, I should say, on the Moon. The Moon, the day is 28 Earth days long. So you're for 14 days of illumination and 14 days of darkness. Yep. So the Moon is particularly difficult. Most of the landers, the small landers are going there at the moment, will literally only live for 14 days. Or maybe they can wake up again, so some of the, if they survive. One of the challenges is power, and the long-lived rovers and other things use not nuclear power, but radioisotope power to stay warm, keep toasty in the cold of the night, and some of them use it for electricity, to generate electricity as well. So energy and power in exploration is a big, big deal, because it can't just use solar.
Thanks very much, and a great talk, thanks.
You're welcome.
As the question's slowing down, perhaps I'll permit myself one.
Of course.
As you're an engineer, I'd like to know a little bit about how far the Artemis program is planned. Are there milestones? Is there a critical path? Does it end with a rocket to Mars?
It doesn't end with Mars, no. I mean, it is we are planning missions out to Artemis 6 and 7 at the moment. So, gosh, I have to remind myself. Artemis 2 is the first crewed mission. It's a free return round the Moon and back again. At present, Artemis 3 is intended to be the first landing. Artemis 4 and 5, assembly of the gateway. Artemis 5 and 6 will also include astronauts on the surface of the Moon. We are have our industry under contract up to Artemis 6, and we've just received the contracts for 7, 8, and 9 service modules. The contract's not yet placed with industry. There'll be a negotiation. And that will take us into the early 2030s.
You can have milestones, of course, which aren't funded.
Yes, absolutely.
Sort of
Yeah, absolutely.
I'm sorry, there was a question at the back.
But critical path at the moment goes through the human lander system,
Okay.
and that it doesn't exist right today.
Thanks. You referred briefly to the problems of zero gravity on the human body.
Yep.
What solutions and what sort of engineering solutions might be considered for?
Okay, well, of course, if you know your science fiction, there's the idea of building giant spacecraft that rotate and generate artificial gravity. We're not at the engineering or launch capability to do that, but there is plenty of work that's being done on so-called short-arm centrifuges. Take a step back. Our astronauts now that go to the space station sometimes come back fitter than they were when they left in terms of muscle strength. They spend so much time on the treadmills and the other exercise machines. Alex Gerst, the German, told me that he was stronger when he came back. What we have not solved is the bone density loss, the loss of material out of the bone, and the thing that has come to light relatively only in the past 10, 15 years, which is changes in the cerebral fluid. And the way that moves around in the head and the cranium and distorts the eyes in particular. So some astronauts come back with modified eyesight because of the squishing pressure. I'm not a medic, but let's call it the squishing pressure on the eyes. Some of them it returns to normal, and some of it they don't have permanently altered. It's not enough sample data to fully understand the problem now. One of the most outlandish things that is nevertheless being considered is that there are certain animals that can go into a state of torpor, where it's not hibernation, but it is a state of lowered circulation and lowered temperature. And the question that we're just starting to think about the question as to whether humans can be put into a state of torpor that would reduce their consumption of oxygen and so on, and survive the journey in that state. Again, it's not the cryogenic hibernation cells of science fiction, but it's the question of torpor is not science fiction. So yeah, and then there is the whole question of cocktails of drugs and various kind of biomedical solutions to the problem. So the answer is going to be a combination of all of the above, I think.
Final question.
You mentioned the word lake when you mentioned Mars.
Yes.
Are there any sedimentary rocks on Mars?
Yeah, that's exactly what we think we see from orbit are indeed sedimentary rocks and river deltas. Implies that I'm not talking about current lakes. I'm talking about lakes 4 billion years ago, ancient riverbeds. Yes, I mean, if you want to look at it, I have a book at the front here, which is imagery from our ExoMars orbiter, and you will see every kind of terrain on the surface of Mars, and clearly ones that have been affected by water, other ones have been affected by other geological phenomena. Of course, we have the enormous old volcanoes on Mars, much bigger than Mount Everest. It's an incredibly complex geological environment. But yes, the logic of the missions, both where the Perseverance rover is seems to be about a 3.5 billion year old riverbed estimate. We'd have no absolute data. That's exactly why we're going to the places we're going to, are places where water once flowed.
David, I'm going to bring it to a halt there. And once again, thank you so much for coming and speaking to us. I know you've come all the way from Bristol, not from outer space, but from Bristol to give us a talk this evening. And I should be absolutely mortified if you missed your train coming back. So thanks once again for what has been a brilliant presentation, and all the best for the future plans and space projects from the Netherlands.
Thank you.